So in this video, I'll discuss energy diagrams, which are also referred to as energy reaction coordinate diagrams, and how we can obtain information based on the analysis of these diagrams. So before we start analyzing, we need to make sure we're able to understand what the diagram represents. So what are the different parts of the diagram and what information does that give us? So here we have a reaction diagram. It doesn't show the exact amount of energy, but generally you'll see your energy on your y-axis, or that vertical line, and on your x-axis, the horizontal line, you'll see it labeled as reaction coordinate or reaction progress. It simply shows us what happens as this reaction takes place. Recall, in a chemical reaction, you start out with something known as your reactant or your starting materials. Those reactants, whether you have more than one or only one, the reactant or reactants of a reaction then go on to produce products. And so anytime we're dealing with a chemical reaction, we're showing the process in which our reactants are forming or being generated into products. And so for the reaction coordinate, and again you may see it referred to as reaction progress, it's simply showing us the process in which the reactants are converted to products. So if we keep that in mind, that means that we're starting with reactants and we're showing how those reactants are converted to products. And so the left side of your reaction coordinate indicates information about the reactants. The right side indicates information about the products. How we go from the left to the right gives us information about the chemical reaction and an energy associated with the change going from the reactant to the product. And so here we have a reaction coordinate diagram that is labeled with different parts. And if we look at the different parts, the part labeled as 1 goes from our baseline up to this point. Now this height will vary depending on what your reactants are, what your chemical reaction is, but regardless of the fact, this first portion of the reaction coordinate diagram gives us information about the energy associated with the reactants. So I'm going to just call it reactants energy. So it tells us the energy associated with that starting material. Again, that value will vary. From there, we can then gain insight into what's happening as this reaction continues. And as we move on, if you notice, this curve starts to climb. So you start to see an increase in the energy because we're going from down here where our reactant energy was, and we're going up a hill. We climb that hill to the very top of that hill. So this highest point of the curve. So the part that is labeled as 2 is showing us the energy difference from our reactants, or from that line to the highest point of this curve. The highest point of that curve indicates at this point we are now transitioning between our reactants and the products. So you'll hear that referred to as your transition. And so during that process of chemical reactions, you have old bonds that break so that new bonds can form. Breaking bonds requires an increase or an absorption of energy. So as we climbed up the hill, that was the process in which bonds were being broken. Once we get the bonds broken, then the new bonds can form. When you start to form bonds, that releases energy. So the part that is labeled as 2 shows us the energy associated with breaking those old bonds. And again, once that takes place, we can then start to form those new bonds. Keep in mind that chemical reactions represent a chemical change. Chemical changes indicate a change in composition. So now that those old bonds are broken and new bonds are now ready to form, we're going to start to see a change in the composition of matter. And so that difference between the energy associated with your reactants and that highest point of the curve is known as your activation energy. The activation energy is the minimal amount of energy needed in order for this reaction to now form the product. So in other words, it's the energy needed to break those old bonds so that the new bonds can now form. Activation energy, sometimes you'll see it referred to as EA, or E with A as your subscript. And again, that's just the minimal amount of energy so that our new bonds could then form. And so that difference from the reactant energy to that highest point, so what's labeled as 2, represents your activation energy. Once the activation energy has formed, once we've overcome the activation energy, so we now have that minimal amount of energy needed, then you start to form new bonds. And again, when bonds are forming, they release energy. So you start to see a decrease. The energy starts to decline. It goes down. That decrease in energy will vary in terms of the amount depending on the activation energy and what products are formed. But regardless of how deep that line is, how low it goes down, how high it stays up, that difference gives us insight into the energy associated with forming those new bonds. And so we get to a point where we then reach the energy of our products. And so for parts 3 and 4, they're giving us insight into other components within this reaction. I'm going to skip 3 initially and go to 4. 4 gives us the energy of the products. So it's going to be our product energy. So I'm going to just call that products energy or energy of product. So that gives us the difference between the baseline and whatever the energy of those products are. Again, that will vary depending on what the product formation resulted in. I say 3 for last because 3 gives us insight into the overall reaction. So 1 tells us information about what was present before the reaction took place. 2 and 3 are telling us about what takes place as the reactants are converted to the products. 4 is telling us about what is present after the reaction has occurred. And so for 3 gives us the difference between the energy of our products and the energy of our reactants. This is known as our heat of reaction. So the heat of reaction, or you'll also hear referred to or shown as delta H. That heat of reaction is what allows us to determine whether or not we're dealing with an endothermic or an exothermic reaction. We have to look at products minus reactants. So delta H, I'm going to just say P minus R. So the energy of those. If your products have a higher energy than your reactants, then that means you're going to have a positive delta H. Positive delta H indicates that you're dealing with an endothermic reaction. If you have a lower energy for your products than your reactants, you're going to end up with a negative delta H, and that indicates an exothermic reaction. Endothermic reactions mean that as we went from the reactants to a products, energy overall was absorbed. And so even though you're going to always see absorbing going to your activation energy and then releasing as the new bonds are formed, we're simply talking about the difference between the reactants and the products. So when you look at this energy and this energy, when you do this P minus this R, if it's positive, it's endothermic. If it's negative, it's exothermic. And so you can look at it and just gauge whether or not it's going to be positive or negative, just looking at the height levels. If your reaction coordinate diagram does not give you values. So this one does not give values for the energy, but we can see that the product side is higher than the reactant side. If you need to just put some random numbers here just to show, so I could just call this 0. I can call this 10, 20, 30, even though my scale is off. I'm just putting random numbers there because I know that this value is increasing as it moves up. So then what that tells me is that my product would have been 20. My reactant would have been 10. 20 minus 10 gives me a positive 10. So I'm dealing with a positive delta H value, which indicates an endothermic reaction. So again, I just put those random numbers there, just increasing numbers as it goes up. But these are how we identify the different parts of a reaction coordinate diagram. So let's just look at a blank one again. And again, we could think about the different parts. We always start with the reactants. We always go to the products. The highest point between the reactants and the products represents our activation energy, so that minimal amount of energy that is needed. And then from there, we can look at the difference between our products and our reactants. So we can look at this difference to determine our delta H. Again, because this P is higher in energy than the R, this delta H would be positive, meaning that we're going to end up with another endothermic reaction. So when we're identifying reactions as endothermic or exothermic, it's simply indicating whether or not the products have a higher or a lower energy than the reactants. So again, this one is endothermic. If we do the same thing with this reaction coordinate diagram, we label our reactants, products. Again, that highest point represents our activation energy. And so in order to actually calculate the activation energy, we would be going from our reactant energy. Just draw a dashed line. So from here up is our activation energy. But if I'm just trying to indicate whether or not this is endothermic or exothermic, I want to look at the difference between my products and my reactants. So this difference will represent my delta H. In this case, because my products are lower in energy than my reactants, I'm going to end up with a negative delta H, which indicates I'm dealing with an exothermic reaction. So endothermic, the product is higher. Exothermic, the product is lower than the reactor. So I hope this helps. If you have any other questions, feel free to let me know. Thank you.